All right. So thank you. Thanks to Heuritech for inviting me to talk about Neural Turing Machines. I hope this is not going to be as hard as Charles described it earlier, but I'll make my best to make sense of what Neural Turing Machines are. But first of all, so I'm Tristan Deleu. I'm a data scientist at Snips. So first of all, I'll just quickly talk about what we call memory augmented neural networks. So this is a very new kind of branch in deep learning, especially in sequence modeling. So this is something that is like 1 or 2 years old. And the basic idea is that a neural network, like the way it works, like when you're using convolutional neural networks, recurrent neural networks, basically you take the input, so for example an image, and then you apply some kind of function just from the data, and you give it, and it gives an output. But what ultimately you want to do is to add external knowledge from like something you have learned from experience, such as like boats float on water. You can't sail against the wind, and boats do not fly. So things that typically in your neural networks, for example, if you detect a boat in the sky, like the neural network will say, okay, there's no problem, there is a boat over there. But from experience, you know that it is not the case. This is not happening. So this is something that you could try to give a better explanation of that. So this is what motivated memory augmented neural network, is that instead of adding this knowledge into the neural network, which is very hard, you add this knowledge into a knowledge base, an external memory that the neural network will ping eventually sometimes, so that it is easier to learn. It is inspired by neuroscience, so there are a few people talking about it. It is trying to mimic the way the brain works, the way the hippocampus works, through the creation of new concept that is related to memory. And these memory augmented network, basically the idea is just adding a memory to existing neural network. And this has been very helpful, especially to memorize intermediate computations from existing models like recurrent neural networks. So for example, it has been applied to QA problems, so question answering, where the model reads a story fact by fact, and then it has to answer a question about this story. And the memory is helpful here to remember all these facts. So for example, you have these models that are called the memory networks and the dynamic memory networks that do that just fine. So I'm going to quickly talk about how we apply it at Snips. So if you don't know what we're doing at Snips, we're trying to create a knowledge graph, a knowledge base around you. So from every kind of of data we have about you, so from geolocation data to emails to calendar events or things like that, we want to recreate a knowledge graph centered around you to give you so that you can search this knowledge graph, and then you can suggest things based on that. And the way we do that, we are relying heavily on NLP tasks and natural language understanding as well, so that in this simple conversation, we want to know which phone number corresponds to which contact, which address corresponds to which contact. And this is something that current models don't really handle that well, and that deep learning is hopefully going to solve. We also released, so on the topic of Neural Turing Machines, we released a blog post yesterday about it, as well as a library, an open source library, so that everybody can play with all the examples I will show you today. This is based on Lasagne, which is itself based on Theano. So this is all known, very known stuff. Okay, so the way you do sequence modeling in deep learning, typically you are applying these kinds of models, like LSTMs, stacked LSTMs, or all these models like that. So this is the basic way to do sequence modeling in deep learning. So you have like your input, that is the X over there. So it can be words from text data. It can be part of the sequence from speech recognition, things like that. So this is very well known. And the way we want to augment it with the memory through the Neural Turing Machine is with some kind of pointers that are very low level compared to this higher level architecture. So the way the model is described, by the way, this model has been developed by Google DeepMind in 2014. I should have told that earlier to give credit at least. So this is basically how they present it. So you have 4 main components in a neural Turing machine. You have something that is called the controller, which is actually basically your typical neural network, the way you would use it, that will interact both with the inputs and the outputs. And the way the neural network will interact with the memory is through very, very low level operations that are the read heads and the write heads. So if you're familiar with Turing machines, this is very similar to the way the classical Turing machine works, with a pointer that is going left and right on an infinite tape. So this is typically the way you would do sequence modeling. Just have this part of the neural Turing machine, just have the neural network part that is interacting with the inputs and the outputs, and the neural Turing machine is adding something above that. So the way it works, so this is this is taking the input data sequentially. So it reads every single item one at a time. So for example, if I place, if I have the input over there and the corresponding output, that is just by some classical task, that is just copy the input we have into the output. And keep in mind, this is not an autoencoder. We don't see the whole sequence at once. We see it one by one. So you first have to memorize it and then write it back from memory. So you have the neural Turing machine that reads one item, then the next one as well, and then goes through the sequence until it reads some kind of end of the sequence flag that is represented over there. But the model doesn't know that it's an end of the sequence. It has to figure that out from the training data, and then from memory it has to retrieve all the items from the input sequence. So if you remember the graphics I showed earlier, this is compared to the LSTM. This is the neural Turing machine as you unfold it through time. So basically, these are the 3 components, and the memory is represented by M, and the controller can be either a classical neural network, such as a feed-forward neural network, or it can be a recurrent neural network. We'll see that after. So the controller at each time step receives an input and something that is called the read vector. That is something that is it has read from the memory, and the controller will output both something to write on the memory and then something to read from the memory. So you have these mechanics over there. If you want to use a recurrent controller, you can. It will add a lot more complexity to your model, but it will also be a lot more powerful for your tasks. So I will explain in more details how the Neural Turing machine works inside, how it updates its components so that it can learn basic algorithms only from training data. So we have two heads, like two main types of heads. You have the read head, that means that it reads from the memory. So you have the memory that is on the left-hand side, and the read head will output weights will output a vector of weights that it has to read from the memory. So here, just to output the read vector, it has to make a weighted sum over all the memory based on the weights from the head. So, for example, here we are mainly focusing on the second row over there, and the read vector is going to be this one. Then for the Righthead, so this is something that is very similar. You have the Righthead that will get a vector of weights, and the controller will give it something to add into the memory. And here we are just adding at the memory location we have focused from the Righthead the vector over there. So this is interesting, but something that is very interesting in the Neural Turing machines is that you can train the whole model end-to-end with like your favorite stochastic gradient descent algorithm. So we have to make the updates of the weights from the heads differentiable, and this is something that is very challenging if you think about it. So we want it to be differentiable, and we want it also to be as sparse as possible, so that every operation in the memory is as sparse as possible to make very little change at every time step in the memory. So the controller, so each update will have 4 different operations. The controller will give you a bunch of parameters that are going to feed into all these operations, and I will describe them step by step. So you have the content addressing first, then the interpolation, then the convolutional shift, and finally the sharpening step. So the content addressing is actually very interesting because it's very different from the classical Turing machine in the sense that it will try to make some kind of like if you think about it as a pointer in some programming language. So it will find from a key vector that is given by the controller. It will try to find in the memory the vector the memory location that is the closest to this key vector, and we will do that with some cosine similarity followed by a softmax. And as you can see, the key vector that is given by the controller is very similar to the 4th row, the 4th memory location over there, and the output from this operation puts a lot of weight, a lot of attention on this memory location. Then you do an interpolation operation so that you can either skip the previous step or not. So you can just use the results from the previous time step, and you have an interpolation. Like this is a classical way to do that. Then you have a convolutional shift. So this is the closest to the Turing machine, the classical Turing machine, in the sense that this is where the pointers in the heads, the weights in the heads, will shift either left and right based on some parameter S that is given by the controller. And the convolutional shift will just do a convolution over your weight vector that was given by the interpolation step, and then will shift everything, like in that case, will shift everything left. And finally, you have a sharpening step that is a way to still be differentiable, but to put a lot more focus on the most relevant weights. So think about it as some kind of softmax if you want. So to sum up what we did in these 4 operations in this example, we went from this weight Wt minus 1 to this weight Wt, and basically if you think about it as a high-level programming language, we just did a go-to pointer and then shift to the right. So this is and note, remember that every step was differentiable. So we can learn this program just from training example and stochastic gradient descent. So the way you training afterward is that you feed it. You feed the Neural Turing machine as much training data as possible. So you have the input, that is your input sequence, and then the expected output, which is the output you get from the algorithm you try to learn, given the inputs. And in this graph, I'll show you the input we give the NTM at every step of the training, the output from the Neural Turing machine at that time during the training, and the error from the expected output. And as I'll show you as well the memory usage from the Neural Turing machine and the way the heads are used. So you'll see how the Righthead is used and how the Righthead is used. And as you can see, as it sees training examples like that, it learns very fast how to use its Righthead to write things in memory and then try to read it from memory, just like that. And in just a couple of, in this case, it's 2,000 iteration with 2,000 training examples. It learns how to copy perfectly one input sequence into the output. And then you can try it on your test data. So the test data, this is very interesting because we don't want to just learn from the training data. We want to learn the algorithm. So we wanted to generalize to longer sequences. And this, in this example, we have an example that is 3 times longer than what it saw during training. And as you can see, it still can figure out the algorithm that is learned by the Neural Turing machine. So we have a couple of other examples. I will skip them. I also have the repeat copy task that is very similar to the other one, where you repeat, like the Righthead repeatedly goes through the memory that was the things that were written in the memory previously. So we have a bunch of other examples. If you want to check them out, you can go to the blog post if you want. So to conclude, what did we do? Basically, we went from an algorithm to learning an algorithm by some kind of models, and that kind of seems to be a bit convoluted because, like, you could have just programmed the algorithm in the first hand. But what is very interesting in this case is that it can give some hints about how the humans try to learn only from example concepts, whole concepts, because if you think about it, the algorithm for the computers, the algorithm is kind of a concept for a human. So this is the new way to get into artificial intelligence. It's to teach the computers to learn things the way we would do, but these tasks they are really good at. Thank you, and if you want to check them out, go to the blog post and the code as well.
Any question?
Yes?
Yeah, I was wondering how hard is it to train? I mean, how hard is it to make it converge? Yeah.
So it is very hard to make it converge, actually. You have to use very sophisticated stochastic gradient descent procedures. In all of these examples, I used Adam, which is something that is now typically used for deep learning. But this is not only the drawback we got from learning neural Turing machine, as what we really were interested in is not only to learn training data. This is actually kind of simple, to just learn training data, but to be able to generalize to longer sequences, to things that the model has never seen before and never been close to seeing that before. This is actually very challenging. You have to fine-tune all the hyperparameters, and we went through a bunch of experiments to get the right one, and I think we have things that are very, very powerful now. Yes?
Could you speak a bit about the initialization? Is it important? Are there ways to make the initialization flat or it down?
So there are two things to think about when we are talking about initialization. There are like all the weights from the matrices, like the classical way we have, like just in LSTM, for all the updates we have. There are also, so this is like, I didn't really check in this case. I used random initialization for most of the parameters. What was very difficult though was the initialization of the weight vectors for the head, because you want to first get weights for the heads to be like very sparse, and this is something that is very difficult to learn to learn by examples. So in these cases, I just fixed the initial weights to be like the first position in memory, and like it did work well. I'm not really sure that like it would make more sense to learn them from data, but maybe we could. Yes, one last.
Okay. For the recurrent port layers, did you try instead of LSTM GRU?
So I didn't really stress test every single task on LSTMs and GRU. I have both implemented in the library, but like I didn't get any better results from either of these ones compared to the feed-forward one. That is the one we used for most of the examples in this presentation. Like for these very simple algorithmic tasks, feed-forward controller was okay. It was okay, and it was actually quite fast to compile compared to a recurrent controller, which is important if you're doing multiple experiments.
Thank you very much.
So next speaker is Vincent Gire.
Thank you, Charles, for giving me the opportunity to practice my English. I'm not a researcher, I'm an entrepreneur. I created a company specialized in ad optimizations with semantic analysis, and which was sold to Page Jaune a few years ago, and I'm now creating a new company focused on artificial intelligence for voice calls. So I'm building a team and I'm looking for good tech guys, so or girls. So if you're interested, we can meet after the talk. So today I'm going to speak about hyperparameters research, which are really important for machine learning and especially for deep learning, because there are a lot of them. So here a few of them, but you have also specific ones for specific algorithms in text analysis or image analysis. They can be also highly counterintuitive. So for myself, I discovered that after a week of fine-tuning hyperparameters, making a mistake which really improved my results. So at this time I was at the same time happy to have better results, but at the same time a bit depressed to realize that I really didn't understand anything about these hyperparameters. And this is a task which is really highly time consuming, because you have to sit behind your experiments. You cannot really change it while it's computing. Because you can mess up the results, and so I'm sure you have experienced this time-consuming task of hyperparameter research. So the good news is that if you're not like a PhD focusing on the same architecture for the same problem during 3 years, we are basically the same as a random search for hyperparameter research. So that's not really the good news. But the good news is that there is a dedicated research area on this topic, which is based on Bayesian optimization. So basically you define your hyperparameter space for each hyperparameter, you define its probability distribution. So if it's like uniform or a Gaussian, or you can define any probability. And so if you want details, just read the papers and explain them to me after, because it's quite hard. The really good news is that the researchers have shared their code. So you can use, for example, Hyperopt or Spearmint. Spearmint, they went further and created a company, which was WetLab, which was cloud-based and added really nice features such as parallel computation and also really nice reporting to help you find the best hyperparameters. The bad news is that WetLab was acquired by Twitter last summer. They closed the service, and they changed the license to be academic only. So I started to use Hyperopt, but I really missed the features of WetLab. And so I decided to create this feature again and to share them with you for free. And this is what I call Oscar. So it's based on the Hyperopt under the hood. You can set it up in a minute. When it's set up, it can run automatically in parallel. You can launch it on a private cluster or on any cloud instances. And you can take advantage of spot instances. And you get really nice reports to see which hyperparameter is working, why, and so you win a lot of time. So let's see a very simple example with just one hyperparameter, x. So we'll try to minimize x squared. So can someone give me the answer to see if you're not all sleeping? Nobody? Okay, I've heard a 0, okay. So that's it. Yeah, that's not a really good example because you know the answer, but it's just to show you how you would do that with Oscar. So it's really the same for those of you who know WetLab, it's exactly the same principle. So the first time you use it, you have to install a client depending on your language. So in this case, it's Python. So pipe install Oscar GitHub. Then you just set up your API access key, which you get on the website. Define your hyperparameter space. So I just guess that x might be in between -10 and 10. And then I will ask Oscar to suggest me an experiment. So he will give me an x, which I should try then in my algorithm. So here, in fact, I should do like a complex Turing machine learning algorithm. And then after this step, I tell Oscar which result I got. So he can use this result to suggest me a new experiment. So in this example, we just ran it 10 times. And this is the result. I'm not sure if you can see, but we can see that it's much better than random search, because in 10 examples, he gave me 0 with 10 power minus 4 precision. So does it really work in real cases? Because this is really a toy example. So I took the memory, the end-to-end memory network by Facebook, which were, the code was shared by Facebook. I read the paper, so basically after one reading, I didn't understand anything. And so I just took their code, changed the beginning of the code to describe the space of the hyperparameters, ask Oscar to suggest me a set of hyperparameters to run the code, their code, and then at the end, tell Oscar which result I got from this particular trial. So in this case, we have 8 hyperparameters. I run that on 10 instances on Amazon. So the good thing is that you can use the experiment. Each time takes 1 hour on one instance. So I could use spot instances. So I got more than 100 trials. In fact, I slept a bit late this day, and it cost me €8. So that's really cheap. And so this is the result. This is just an extract from the Oscar report. So we have all the hyperparameters. The best one is the first. And we can compare that to the results of the paper. If we compare sets of hyperparameters with overall the mem size and the same number of hops, because it's very important features of the architecture. And so we got with Oscar, it's a bit the same perplexity. So we didn't beat the results, cannot say that, but we could find really good hyperparameters for me without knowing anything about how really it works, how really the architecture or the algorithm works. So since this time, I don't try to fine-tune my hyperparameters. If you have an architecture which you really know and you are specialized in that, you should maybe try to continue to fine-tune your hyperparameters. But in other cases, I would try, if I were you, to use something like that, not necessarily Oscar, but Hyperopt or Spammint, because you can really win a lot of time, and it's not really an interesting task to look for these hyperparameters. So you can try Oscar if you want on this website. I had a Python and Lua clients, and Nyland built already a MATLAB client. Now just the clients are open source, but if someone wants to contribute, I would be really happy to open the backend, which is just Hyperopt plus the experiment saving, and the front end, which is all the part with the reportings. Thank you very much.
just wondering whether it also takes into account runtime, like because it knows and possibly predicts from your hyperparameters whether it takes long or not.
No. It's Hyperparameter doesn't take it into account, so I'm not trying to change anything from the underlying optimization algorithm. But if someone was interested, we could plug something else as a backend. That just like we could use different backends, but at this time, no.
Yeah. Two questions. First on Hyperparameter and then on the NATO. On Hyperparameter, I didn't see in your code. I thought you had to define also the distribution of your space of hyperparameters to reach it.
Yes.
And the second thing was objective functions. But I didn't see that in your code. And the second question is about, have you looked at other approach? Because you said it's in research area at the time, that's true. And on, for instance, AutoML that I'm a bit involved in, there is some people from, some researcher in Freiburg that did some stuff like they called auto-scikit-learn or auto-weka, such things. Have you looked?
Well, so for the first question, in fact, first question was where do I define the distribution of the hyperparameter in my example? So in this example, I just when you don't define a distribution, I assume a uniform distribution. And the second question was, did I do like state-of-the-art analysis of all the possibilities to optimize the hyperparameters?
What people from Freiburg did with auto-scikit-learn?
No, because I ran that, and when I saw the results, I said, okay, for me that's enough. I'm not going to optimize the optimizations algorithm, but that's something that would be interesting. And as I say, it's a bit like the same question. We could plug other backends if it's better. I don't want to spend too much time on that. I already want a lot of time running that, running my experiments like that. But maybe, yes, there are better algorithms, and it's a moving research area, so I'm sure there will be better algorithms.
Thank you.
Thank you.
Thank you.
Je comptais faire la présentation en français, mais j'ai l'impression que tout le monde fait en anglais, donc je vais essayer de m'entraîner en anglais. So today I'm going to talk about what we do at Nyland and how we use deep learning for music recommendation. So I'm Aloïs Gruson, and I'm doing the machine learning stuff at Nyland. First, who we are. We are a young startup founded in 2013 by two PhD, Christophe Charvillet and Damien Tardieu. They both worked at IRCAM and they won the challenge in music information retrieval in 2011 in music similarity estimation and music classification. And today we sell our technology through an API, and we are a team of 9. What we want to do, we want to create an high-dimensional space where each song is a vector, so we can use this space to find similar songs and classify automatically these songs into to give the instrument in the song or to give the genre of the song. And we have the constraints that each query must be less than 50 milliseconds in a database of millions of tracks. So how we did it in 2011, back then we extracted short-term features from audio, short-term features like MFCCs or more rhythm short-term descriptor like fluctuation patterns and many more. And we used pooling techniques to transform this short-term descriptor into one vector for each song. These pooling techniques are highly tuned pooling techniques like vector quantization, this one is simple, but also GMM supervector or VLAD or Fisher vectors, the same in images. That was state of the art in 2011. For this presentation, I will show you results on one chosen dataset. We have like 10 datasets for evaluation, and I'm gonna use one metric that we usually use for evaluation of search engine. We have precision at K or mean average precision. Precision at K, it means when you look at all the tracks, and when a track is, for example, a rock track, you want to find rock tracks in the most similar. It means we look at the first neighbor, the most similar tracks, and you want it to be a rock track. That's an easy example for rock. This dataset is 8,000 tracks, and it's in 140 playlists that are mainstream musics. That was state of the art in 2011. In 2013, Nylon was created, and we had first to make a product from research work. And those who tried it know that it's not an easy task. We have done a lot of work on short-term descriptor and pooling techniques since then, in 2013 and 2014. And we have this improvement, something like 10% improvement in this year, in these 2 years. The interesting part is that the whole thing is unsupervised. You give example to learn the model, but you don't give any label to learn it. So we wanted to match, because our clients want to find the idea of similarity in the result of the algorithm. We wanted to match the human perception of similarity with the output of the algorithm. So the first idea that has been applied in the field is to learn the output of a collaborative filtering model. That is you have users, you have a matrix of user and song they listen to. You put it you can get from it a space where song are vectors, and then you take the signal, and with your deep learning you match with a
mean squared error, sorry, you match it. The problem is these algorithms of collaborative filtering are not perfect. So you have a representation that is not perfect to learn from, and also you have to have this matrix of user and songs. What we tried at Nylon was to train a network with group to classify tracks into groups or similar tracks. So we have a client that gave us like 3,500 team-based album. That's one. Sorry for the numbers in English. And each album represents a genre, a mood, or an usage. And this is important to think it as each of this album represents a human ID of similarity. And so we learn it. First, we use a previous system and use the vector from a previous system to learn this classification. And then we remove the classification layer, that's it, the softmax and the last fully connected layer. And we have an embedding space. This one is supervised. And there you can find the results. This one is unsupervised, and this one you had deep learning with this classification and this removed classification layer. And you see the improvement. That's it. On the first similar, that's a good improvement of nearly 20%. And then the most impressive improvement is in the long distance similarity, with nearly 40% improvement. Then you ask, we're in deep learning meetup, and you don't want to have handmade descriptors and handmade pooling techniques. And we ask ourselves, can we do the same they did in images? That's convolutional neural network. And how we use it for music? Music, we have a MEL spectrogram, for example, that's a time frequency representation. So you have to be careful, that's not the same as the image. In image you have width and height, and the square filters really make sense. In music, as you have time and frequency, these two axes have different meanings, and you have to ask yourself, do you really need to use square filters? And the second main differences with images is that you have a big temporal axis. For example, if you take a 30 seconds song, you have an input of this size. So that even with temporal convolution, you still keep a big temporal axis at the output of this convolution. And if you think about it, you want to have a certain time invariance. So the best idea seems to pull along time axis. So this is from a blog post from Sundar Gilman he did at Spotify, and in this case he's learning with mean squared error the output of a collaborative filtering algorithm. So you have here the frequency axis and here the time axis. So you see that in the first convolutional layer, it takes all the frequency axis, and the next convolution are only temporal convolution. The second difference I mentioned is the global temporal pooling. So it uses a function like min, max, and head2 norm, and two fully connected layers. So in our case, we don't use mean squared error, but we use a classification objective here. Some ideas to slightly improve it. We have found that a multi-scale pooling is a better choice. That means here it only pulls the last convolution layer. You can pull also this layer and use it as input for your fully connected layer. we can reduce the max pooling if you have the computational power. And you can add recent advances like batch norm from Google. And these are the results with a fully learned convolutional neural network. You match the results of our system plus the deep neural network here. So you might say that's not really impressive, but you have to remember that our previous system was a combination of 6 highly tuned short-term descriptors with their pooling techniques. That's like really a long time of research. And now with our data, we can use them to learn automatically this descriptor. So this sentence is not quite correct because you still have to work on architecture, sorry. But that's a big change, I think. And you have to remember you used techniques like Fisher vectors, for example, and now you just have a min function or max function that gives pretty good results. Okay, so we can see that the network is able to learn through all these functions. Even the combination of all three is better. These are pretty good results. Also to speak about square filters, they also work. We have to find maybe something else. You have to think about how you want your filter to be. The main thing is in computer vision, when you have an ImageNet network, you can use the features, the convolutional features, to learn other tasks, to use it for classification on another data set. And I think we learned a model that can be used for other tasks. For example, we have another data set that's completely different. That's music for movies or ads, and we have still very good results with our convolutional neural network. To finish, maybe, we use the spectrogram, which is still an name-tuned short-term descriptor. Maybe we could learn directly from audio. This has been tried by Sander Gilman in end-to-end learning for music audio, or by Google for speech, so that's a bit different. That's what they did. So you learn temporal filters here, and you do a max pooling to match the shape of a mail spectrogram, for example. So now we tried it, and that gives worse result as spectrogram. So maybe our training set is not large enough. How we can improve? We try a shorter experiment, and the results are really lower. So maybe if we try with 1500 K tracks or 1 million track, we would have better results. We tried to add more layers with the paper of Microsoft, who won ImageNet recently with deep residual networks, and we got slightly improved results with 78 layer network. Just to conclude, what we could do next is use data augmentation, like in images. You have to find the augmentation that keeps the label, but we have to find the transformation that makes sense in music, simply. We can use recurrent neural network, Siamese network, to learn directly from similar pairs or dissimilar pairs. And then we could use, as usual, more data, or use semi-supervised approach, like ladder networks, for example. Thank you for your attention. you can try it yourself on demo.nylon.io on SoundCloud. And you have tagging and similarity.
Thank you. Any question?
For the collaborative filtering, did you try the alternate software as used in Netflix remove recommendation?
No, we didn't really try collaborative filtering since we don't have this matrix of user and songs that only streamers have. We could ask our client to give it to us. We will do that, but our approach seemed much simpler and it works. But we will try to do that.
You mentioned the work of Snips and especially the work on working directly on the sound signal itself.
Yeah.
Have you tried this? To reproduce what you have shown in this paper on your data set, and what you get on the cold start, especially?
What do you mean cold start?
When you don't know so much about a user or something like that?
We don't have user there because we don't use a collaborative filtering model.
Yeah, but if you want to recommend music,
Yeah.
you have to
Yeah, you have this.
compare.
Yeah, you have the similarity space, so you can do similarity, and this similarity space is learned to match your.
You said you learn by training on collaborative.
No, we didn't do that. Sander DeLeu did. We didn't. We learned a classification task and then remove the top layers, the classification layer, and use this layer to get an embedding space.
What you have done worked pretty well on when you don't know anything.
Yeah, totally. It's work on everything. You can put every song in as an input to the CNN, and then get the vector corresponding to that track.
What is your training set to know similar songs? What do you
That's a client who gave us this one here. Sorry. That's 3,500 theme-based album. That means that can be moods or inspirational, for example, indie rock, or I don't know, something like that.
So you have a score of similarity between every song of every
No,
album?
not score of similarity, but you have these tracks are into each track have an album, which is a genre of or mood. So you don't have similarity, you don't have similar pairs or dissimilar pairs in this dataset. Not really, you have to. That's a classification task.
You say you are right when the similar things you find are the same mood, for instance.
Yeah, that's in that's for the evaluation dataset. Yeah, you have to make that assumption that when they are in similar in the same album or playlist, they are similar. That's the only way you have to evaluate similarity.
Are there any pre-trained models like image?
No, there's no pre-trained models because no, there is no. Yeah, but we said it.
Did you look at the layers? Like what kind of features do you get?
No, if you want to look at what the first layer in the CNN learned, you can look at the blog post of Sander, but I haven't found the time to do it now. But he did pretty well.
Yeah, no, because I've seen his posts.
Yeah, but we didn't do it yet.
Okay, thank you again.
So that's it for today. Thank you, everyone. We have small food and refreshments, and please everybody take your chair, and so that we don't have to do it, and we'll have more room to talk. So please take your chair and put it on the side.
Ça va bien.
Et là, c'est sur la voix chantée, donc lui, les en fréquence, ça marche super bien parce que les plus ou moins c'est mieux. Il reste tout à fait à
C'est exactement là, mon terre. T'as vu? Ouais, pas mal. Un peu bon, mais après ça va, j'ai plus rapport. J'avais vu.
Ça y est, tu démarres le virage vers le machine learning directement. Ah, c'est bon ça.